Okay, so we'll go back to another video. So here we have the definite integral from 0 to pi over 2 of the natural log of 49 sine squared theta. Add this with 81 cosine squared theta d theta. So I think from a first glance, a straightforward attempt might be applying U substitution, maybe, for example, using our substitution of what's inside the argument of our natural log, differentiate both sides and replace it with a new differential to get a new different integrand, but doing so is just going to make things a little more deceiving and convoluted in that sense. So what would we have to do to tackle something like this? In the title, we're basically just going to be using a bunch of trig substitutions, trigonometry properties, and follow with a bunch of natural law properties as well, follow with this ln. And it actually comes down to a pretty interesting result that I think it's going to be nice. And one of the steps I'm giving the spoiler away is that we're actually going to be defining a integral, then calculating that integral, then plugging in back that number such that it'll give us exactly the value of what was the original we wanted to calculate this whole time. So with all that stuff, let's actually now just jump right in. So of course this is going to be called capital Y, we'll just let that be that way. So what we're going to do for inside our argument is we're actually going to change this up a bit. So notice that 49 sine squared theta, add this with 81 cosine squared theta. In other words, I can actually write this as a sum such that together it actually adds to 81 cosine squared theta. So what can we put? So I'll put this as 49 sine squared theta, so that's going to remain the same. And then we're going to add this with 49 cosine squared theta, and then add this with 32 cosine squared theta. What's nice is that because we have a sine squared theta plus a cosine squared theta, we know that fundamental trigonometry that's going to equal 1. So let's factor out with the 49, so that'll actually just lead us to 49 plus 32 cosine squared theta. So that will be our new integral that we'll be tackling along. So capital I is going to equal 0 to pi over 2 of the natural log of 49, add this with 32 cosine squared theta, and then follow with d theta. Okay, so here's where the part I said that we're actually going to define a function of this integral, then calculate that generalized integral in order to help get what we need to do. In other words, in the end, after we get to what we want, we just plug that number back in, and then that's our answer / value. So we're going to actually call this f of a. So f of a will be our following function / integral that we're going to be calculating for this generalization. 0 to pi divided by 2 of the natural log of 49, add this with a times cosine squared theta, and then times d theta. So in other words, we know that I is going to equal to f of 32, since 32 is in that substitution that we placed with back over here. All right, so this is what we need to figure out, and then in the end, we can just plug this back in to get our value. So let's actually just get right into it. Let's take the derivative of both sides, and using famous trick, I'll differentiate inside of our integral. So I have that f prime of a is going to equal to 0 to pi divided by 2 of the partial derivative del, and then del a of ln of 49 plus a times cosine squared theta, and then d theta. And this is pretty straightforward to do, that you'd actually just use the definite with the derivatives of the logarithmic function. That'll get us that this is the derivative is going to be 1 divided by this input, and then we just multiply with the derivative of the input as well. So yielding us with the following. We'll now have 0 to pi over 2, and then now this is going to be cosine squared theta on the numerator, and then divided by 49 plus a times cosine squared theta, and then just put it as d theta. So now let's actually do a little bit of some simplifying. What I can do is I can actually factor out an a, and now I'm going to add and subtract a 49 on the numerator. So now this will yield us 1 divided by a, multiplied with the integral from 0 to pi over 2 of a times cosine square of theta, plus 49, subtract 49, and then under the denominator we'll have this is just 49, add this with a times cosine squared theta, and then follow it with d theta. So as you can see that we have a 49 plus a cosine squared theta, then same thing over here. So what we can do is I can actually split this up using some linearity, so we actually have a difference since there's a minus in here, so a difference of integrals. And of course with that being with the 1 over a had to be distributed as well, so now we'll have that this is going to be 1 divided by a. Let me just draw a bracket over here. So we'll have the integral from 0 to pi over 2 of just d theta, since 49 plus a over cosine squared theta. We have this, so that just cancel out to just 1, and then we're subtract with 49 divided by our denominator over here. So the integral 0 pi divided by 2, then 49 divided by 49, add this with a times cosine squared theta, and then d theta. So this is very self-explanatory to calculate, obviously. This is just going to be theta, just plug in pi over 2 and 0, subtract that, and then just multiply this to here. So now that'll just yield us with pi divided by 2a. And then let me actually just distribute the 1 over a to over here and factor out the 49. So that'll just give us 49 divided by a, and then left with just this same integral that we need to figure out how to calculate. This doesn't look like much that we can do, but we can actually, it looks a little difficult, in other words, is what I meant to say for this integral, but we can actually do something a little more creative. Let's actually now multiply a sine squared theta and divide a sine squared theta as well. So rewriting things as a 1. So multiply and divide a sine squared theta. So this will yield us the same. So I'm just gonna leave this as pi divided by 2a. So this is still 49 divided by a. Now our new integral is gonna be written as follow. So after multiplying the secant squared theta to both the numerator and denominator, so that means secant squared theta on the numerator, then now we'll have 49 secant squared theta, and then add this with a under the denominator. So that makes things a little bit easier, because what's cool is that we can actually now apply a U substitution. Now suppose that if I let U equals tangent theta, and we know that du is going to be the derivative of that is going to be secant squared theta, which is very nice. We have a secant squared theta on the numerator just like that. So let's actually now plug this back together. But also, before we get to another step, let's actually write this in a way so, because we need to substitute everything a little bit easier, because we have a secant squared theta that just needs to be substituted back. So notice with this trig identity, I can actually just square both sides. So I have that u squared is equal to tangent square theta. Then just using the identity that tangent squared theta is in other words the same thing as secant squared theta, and then subtract 1, then of course I can just add the 1 to both sides, so I'm back with just u squared plus 1 equals secant squared theta. And so for now, our new f prime of a, simplifying everything else so far, is going to be pi divided by 2a, and then now subtract with 49 divided by a, with now our new bounds of the integral. So change our bounds, we'll still have this going to be 0 on the bottom, but pi over 2, we plug this back in for tangent pi over 2, that's actually going to approach positive infinity. If we're looking at this from approaching from the left side, if we're going from 0 to pi over 2 with the new bounds. Then now our new numerator is going to be written as 1 divided by 49, then u squared, just from substituting, u squared, and then minus 1, then distribute that, so now that'll be plus 49, or yeah, plus 1 from over here. U squared plus 1 equals tangent squared theta, then the substitution. Then now it's gonna just leave us with just plus a, and then now we're in the world of du. So going even further, I'll factor out a 49 from the denominator, and then that'll just leave us with just a positive 1 on the top. So pi divided by 2a, subtract 1 divided by a, integral from 0 to infinity of 1 divided by u squared plus 1, and then add this with a divided by 49, and then du. As you can see that we actually have something in the form of the integral from, if you check from your integral table of integrals, this is actually in a nice form such that if you take the antiderivative, we get something of an arctangent. But make sure you actually use your right substitution. So by applying from that, we have that our antiderivative of our integral over here. So this is going to be 1 divided by a. Then actually now, if you use this correct and actually taking another step further, simplifying that out with the right substitution for this new numeric square. So now we'll have that this is going to be 1 divided by a times the square root of 1 plus a divided by 49. And then now just multiply with arctan of u divided by the square root of 1 plus a divided by 49. And then now just evaluate this from your bounds from 0 to positive infinity, which of course, if so, you're going to get that this whole thing is going to be just equal to pi divided by 2. And so simplifying now even further, we have pi divided by 2a, then subtract pi divided by 2 times a, then multiply with the square root of 1 plus a divided by 49. therefore, that leaves us with that this is f prime of a is equal to this following. So let me actually leave now and underline what we have established. So now what's left is that, of course, this whole time what we want to do is we want to calculate the generalization for f of a of this integral and then plug this back in. But that leaves us with the derivative. Very nice to say that it just comes down to a nice form for this derivative. So what we can do, we can actually just take the indefinite integral for both sides. So we're actually back to our start for fa. So in other words, to put it simply, we have that f of a is going to equal to the indefinite integral of pi divided by 2a, then subtract pi and divided by 2a times the square root of 1 plus a divided by 49. And then this is in the world of dA. So this is what we're gonna have to, this is our next step from here. So let me actually get rid of what we have and then start from there. Okay, so far to reestablish, we have gotten to the meat and grind to say that f of a is equal to the definite integral of pi divided by 2a minus pi divided by 2a times the square root of 1 plus a divided by 49 and follow with dA. So the last thing to do, well, the second to last step rather, is to calculate what this is going to equal to, and then we plug in our value for a such that this actually gives us our value that we want to achieve. So the first thing, as you notice, is that pi divided by 2a, that's actually not that bad to integrate because we have that this is actually going to be the form of the natural log. What really is the difficult obstacle is that we have something of pi and then the square root function under the denominator. It's not really a nice form that you might think it's an easy antiderivative to remember by. So we're actually going to start with this derivative, or start with this function and then integrate from there. So to calculate, I'm actually just going to now just take away our focus for pi divided by 2 and just look at it in a form of the following. So we want to evaluate the integral of 1 divided by a times the square root of 1 plus a divided by 49 dA. Okay, so let's actually get to that. So we can actually do a U sub. So we'll let U equals a divided by 49. Then of course, if I just solve things back in, because we have to plug in back for the value of a on its own to get in a new value for a new world of U. So we have that this is the same thing as 49u is equal to a. Now, nicely done is that differentiate both sides is du is going to equal 1 divided by 49 dA. Then, in other words, well, this is not really necessary for me to do this because I could have just done this over here. In other words, this is the same thing as saying 49 du is equal to dA. And so that's great that I can actually put in our substitution. So what's nice is that now I can actually just factor out the 49 from outside of our integral. So it's 49, then multiply with our indefinite integral. So there's going to be 1 on the top. And on the bottom, I'll have 49u. And then we just multiply this with the square root of 1 plus u du. Again, factor out the 49 again, so that'll just leave us with a nice 1. And so now we're just left with the indefinite integral of 1 divided by u times the square roots of 1 plus u du. How do we approach something like this? Well, yet again, we're going to have to apply yet another U sub. So I'm actually going to change this variable so that we're in the world of v this time. So we'll call this the V substitution if you want to. So now, suppose that if we let our substitution v equals the square root of 1 plus u. So I want to solve this in terms of u on its own because we're going to have to go back and replace this eventually. So this will give us that u is going to equal to v squared and then subtract 1. Nicely done that, I'll differentiate both sides. So I have that du is equal to 2v and then dv. Now we just plug this back together. So our new integral now will yield us with 2v and then divided by, so v squared subtract 1 and then now multiply with v, then dv. Then what I can do from here is, well, now the v's just cancel from both the top and bottom, so now we're easily now left with just 2 divided by v squared subtract 1 dv. What's nice is that on the bottom it's can be factored out as a difference of squares. So I have 2 then divided by, well, let me first factor out the 2, and so we're just left with 1 inside of our integral. So now 2 times the integral of 1 divided by difference of squares on the bottom, so it's v minus 1 and then v plus 1, then dv. So this is actually, I'm going to skip this step because all you have to do is just apply some partial fraction decomposition to get things simplified even further. So leave that to you guys as an exercise to verify. What you'll get to that is now this is going to be 2 times the integral of negative 1 divided by 2 times v plus 1, and then add this with 1 divided by 2 times v subtract 1, then dv. So as we know that this is going to be an easy antiderivative to know that this is actually just the natural log, so this is going to be 2 times. Now we have the natural log of v subtract 1, then divided by 2, then subtract the natural log of v plus 1 divided by 2. And so I'll just factor out the 2's. The 2's cancel, and what's left is we have to substitute back in our value for v. So v's, we set this equal to square root of 1 plus u. We set that u is equal to a divided by 49. So we put this back in. So now we have that the easiest to calculate now is that this is going to be the following. This will yield us the natural log of the square root of 1 plus a divided by 49, then subtract 1, and then now this is going to add this with, or rather subtract, the natural log of the square root of 1 plus a divided by 49, and then add this with 1. Now if I just put things together using the properties of natural log, so I now put this together under a single logarithm, it will yield us with the square root of 1 plus a divided by 49, subtract 1 on the numerator, and then under the denominator we have the square root of 1 plus a divided by 49, and then add this with 1. Okay, so that's the nice generalization that we have, that this integral is going to equal this. So now all I have to do is just multiply the pi over 2 to both sides, well, to this specifically. And now we get that applying everything, taking this entire antiderivative, the indefinite integral is that f of a is going to equal to pi divided by 2 ln of a, and then subtract pi divided by 2, multiply with the natural log of the same thing over here, the square root of 1 plus a divided by 49, subtract 1, then divided by the square root of 1 plus a divided by 49, and then plus 1. And because this is a indefinite integral, we have no bounds, make sure to add your c. This is a very common mistake that a lot of newbies from Calculus 1/Calculus 2 get confused with. So now here's the next step, and this might be a little bit of a long one specifically, is we can actually simplify our argument of the natural log over here. So as you're taught when you're dealing with limits of rational functions, you'll have like square roots. You can actually now, to fix this up, we can multiply the conjugate of the numerator and the denominator as well. So I'll actually be multiplying the numerator's conjugate, and this is gonna take a lot of time, and well, when I say a lot of time, I'm not really going to go into that whole detail because it's basically an easy step to do. It's just very tedious from there. So again, I'll leave that to you guys to verify. So if you multiply the conjugate for both the numerator and the denominator, and then you simplify some things out, we'll get that. So I'll just leave this I'm just going to calculate this for a second. I'll just leave this on the side for later. So this will yield us pi divided by 2 times the natural log of, now this is going to be a divided by 49, and then on the denominator I have is the square root of 1 plus a divided by 49 plus 1, and that quantity is going to be squared. So what's nice is that if I put everything back together, so f of a, so far we have that this is pi divided by 2, then ln of a. So what I'll do is I'll actually put the minus first because we're just looking at our denominator from the natural logs and applying the properties of the natural logs. I have a square, factor that out, so that means the 2's will cancel. I have a pi times ln, so this is going to be now the square root of 1 plus a divided by 49, and then add this with 1. And so because that there's a minus, I'll change that sign, so this is going to be a positive, and then subtract, so subtract pi divided by 2, then multiply with ln of a divided by 49, and then now add this with c. Now we can actually simplify some things even further. For one, we have pi over 2 ln of a and pi divided by 2 ln of a divided by 49. And if you subtract that, so I have a pi divided by 2 when we're dealing with natural log properties specifically. So I have an ln of a divided by a over 49. Now if you actually just simplify that out, so I have pi divided by 2 ln of a ln of 49, then just move the 1/2 into the argument, so that's square, so the square root of 49, aka that's the same thing as pi times ln of 7. So yielding us with pi times ln of the square root of 1 plus a divided by 49, add this with 1, and then add this with pi times ln of 7, add this with c. So we have to figure out what that c is going to equal to. So to reiterate, here's a guess and check in order to figure out what our c is going to be. We have that we can choose, for example, 0. So I have that f of 0 is going to be the integral from 0 to pi divided by 2. We said that this is the natural log of 49 plus a. Now substitute that in for 0, then cosine squared theta and d theta. So that means I have ln of 7 basically because this is 0. So if I integrate both sides, I have pi divided by 2 then times ln of 49. Then you just apply the same thing, move that 1/2 inside of the integral. We're taking the square root, so we're just left pi times ln of 7. So in other words, ln of 7 is this side and this side, so I'm actually just going to erase this. I write the whole integral just to do a little bit of reiteration, and also because I just deleted the thing. So now we have that f of 0 is equal to pi times ln of 7. So that's a good way to check. Now, if I just plug the 0 back into this, our generalization over here, so f of 0 is indeed just going to equal to, so let's see, if I plug in 0 here, so this is 1 plus 0, so square root 1 is 1. 1 plus 1 is 2, so I have pi times ln of 2, and then plus pi times ln of 7. And of course, we said that this is actually the same thing as equal to pi ln of 7 for f of 0. So therefore, we know that our c is actually just going to equal negative pi times ln of 2. Okay, so to put things together overall, we have that f of a is going to equal to pi times ln of the square root of 1 plus a divided by 49. Add this with 1. And then now if you actually just put everything together, so pi ln of 7 and then subtract pi ln of 2, and then using law of properties, I have that this is pi times ln of 7 divided by 2. Okay, so we actually found our nice little generalization for f of a. So now the last thing to do is actually just plug a equals 32. And so what that means is that I plug a equals 32, I'll just save the work, that we have 1 plus 32 divided by 49. So if I just get that together, that's going to be 81 divided by 49. Take the square root of that, I have 9 divided by 7. Add this with 1, so that means that's 16 divided by 7. Combine this together with the natural log, so that means pi times ln of 16 divided by 7 times 7 divided by 2. The 7 will cancel, so then that leaves us with 16 divided by 2, aka 8. So far, pi times ln of 8. 8 is the same thing as 2 cubed, so that means I'll just take the 3 outside. And so now that just leaves us with that capital I, aka our given integral, and then this is after plugging a is equal to 32, is going to yield us 3 pi then times ln of 2, which is indeed our final answer for this trigonometric and then natural log integral that we really have to rely on a lot of trigonometry and, a bunch of natural law properties just like that. So yeah, that's pretty cool if you ask me.